Hello everyone. So today we'll be talking about fast sorting and the use of certain specific interfaces, which often come up in assignments. So we talked about interfaces a bit before and about recursion a bit before. So I expect you guys know a little bit about those two things. But we are completely new to fast sorting algorithms. So today that's what we'll be covering. It's the same stuff that we covered in the lectures that were posted. And it's going to be what is, well, you're going to see it later in assignments and you're going to see it obviously in quizzes and stuff. And yeah, let's get right into it. So we're going to use recursion to speed up sorting. So let's talk about what it is to have fast sorting. That's my first slide, right? Yeah, it is. So what does it mean to have fast sorting? What is all that? Why do we have it? I'm just going to move myself out of the way of the slide over here, somewhere into a corner. So we've got merge sort, which is a fast sorting algorithm. And the way it works is it uses recursion to divide our array. So we know that our sorting algorithm needs to take in an array. It needs to output an array that's in order. How do we quantify that? Well, we can see that here we have our array that's out of order. We've got like 38, 27, all those other numbers which are not in the order they're supposed to be. And we're supposed to get these things into order. So 38, 27, 43, 3, 9, 82, all these are out of order. So what merge sort does is it says, instead of sorting this whole big array, all of it, here, we want to sort smaller arrays, right? Because it's easier to sort 9, 82, 10 than it is to sort 38, 27, 43, 3, 9, 82, 10, right? It's way easier to sort this 9, 82, 10 thing. So that's what merge sort says. It says, let's sort the smallest possible division of our array. And to do that, we use recursion. So that to my that direction, kind of messing myself up by moving myself around about my directions. But the thing that I'm on top of right now, this is the process of merge sort, and through this, hopefully we'll understand it a bit better, and we'll be able to progress towards actually implementing merge sort. But before we get to that, I'm going to open it up to any questions anybody might have, anything you're wondering off the top of the session about this or otherwise, before we get into merge sort. Alright, so I'm assuming that means you guys are kind of clear on well, what we're doing, why we're doing it. And if there are any questions that come up, of course, you're welcome to ask, and the chat is also available. So, let's get into it. Merge sort. So, it's a recursive algorithm. That means that we have a recursive call, but we also have other methods there as well. So, we've got a merge method and a sort method, which we'll see in the code. And then we have, as well, it as a recursive system. So it's going to recursively divide our array. So here we start with 38, 27, 43, 3, 9, 82, 10. Then we go right divide, divide, divide. Could somebody tell me what could potentially be a recursive algorithm to divide an array? Just to break it down into individual elements. How could we write such an algorithm? What would kind of the steps of that be? Could anybody maybe think about what that would look like? Maybe I should ask more specific questions. Maybe I should say, what is the base case of a recursive algorithm that divides arrays? So what it does is it takes in a big array, and then it divides those arrays into arrays that cannot be divided anymore. So to break that question down, yes, you guys are saying in the chat an array of length 1. So could somebody come up on the mic and say, what would a base case be for a recursive algorithm that divides an array into smaller pieces? Again, our question is, what is kind of the base case of an algorithm which divides arrays into arrays of size 1? Anybody who wants to is able to speak up, and we can discuss that. Again, we don't care about what we do in the recursive step. I'm just asking base case. What is the base case of dividing an array into little blocks? So in the situation of this division that we have on the slide, what is our base case? I know it's in the chat, but yeah, could somebody come up and explain their answer maybe and give us a bit more detail about all of this? Yeah, exactly. So we only need to divide an array if it's bigger than 1. If we have an array of size 1, it's already fully divided. And actually, if we look at how merge sort works over here, it does exactly that. So at the top, we have our big chunky array. This can be as chunky as we want, which direction is it in? It's that way. It's towards the window. So we've got a really chunky array there, right? And then as we go down, our array gets less and less chunky until we eventually get to the smallest possible arrays, which are arrays of size 1. So all the ones below me right now are our base case. So now that we've identified that, before we even get into writing merge sort, I'm going to hop into Java really quick, and maybe we can write a method that's really simple. All it's going to do is it's going to take a big array, and it's going to divide it in recursively into arrays of size 1. And maybe once it's finished dividing, it'll just go away, right? That can be our first little method, and that's going to actually be a large part of merge sort. So I'll transition away from our slides now, and we'll create a new project. New project. I'll call it merge sort. We're just going to do it from scratch. We'll do an application of merge sort, but not this time. We're going to do that on Friday. This time we're just talking about getting the code running. So merge sort. Right, and we're going to be working with arrays. You can generalize merge sort to work with whatever data structure you want, but for the sake of understanding, the easiest way we can do it is with arrays. So we'll do it with arrays. And I like to say ints. We could compare ints or integers because those are pretty easy to compare. So let's just say merge sort. And then of course we can generalize that as well using an interface later. But right now, we're just going to create a public static void divide. Let's call it that, right? Divide, and it's going to have a integer or maybe an int, boom, array, right? So we've got this method that divides our array. We know that our base case is when we can't divide any further, right? We know that our base case is going to be when the array is of size 1. But how could we divide an array? We don't have multiple returns in Java, right? We can only return one item. So maybe instead of actually dividing our array, oops, what's going on? Instead of actually dividing our array into smaller array objects, is there something we can do to save on memory and also to save with not having multiple return types for our division that doesn't require us to create new arrays? So my question is, we cannot return multiple arrays in Java. We need to divide it, and then we can say it's wasteful to create all new arrays each time. Right? We don't need to create a new array every time we divide. Is there something else we could do to maybe keep track of where we are inside our current array? Now, one of you guys say return a pointer, but we are returning a pointer to the array with this array. Another saying make a temporary variable, but is there some way we could do it where we don't have to actually create any variables? Because remember, we have this array in our memory, right? And we need to access it. But maybe instead of dividing our array literally into smaller arrays, which is kind of what we show in the diagram, right? If we look at the diagram, we do actually literally divide our array. But if we look at how we can implement this in Java in a way that's more effective, what if instead of dividing it, we just think about our indices, right? So if I want to access, for example, this case, 9, 82, 10, from the top array, 38, 27, 43, 3, 9, 82, 10, right? I want to divide the big array into a smaller array. I can also access this. This is equivalent to just saying index, 5 through index 7 in the array, right? 9, 82, 10 is the same as index 9, or index 5, index 6, index 7, right? It's the same thing. So again, and the lower one is actually just saying indexes 5 and 6, and then this one is just index 7. Do you guys see that? How these small divided arrays could actually just be represented as indices inside of the main array. So again, 9 and then 82, that pair, is equivalent to just saying that it's the first array at the index, 5 and 6. Does that make sense to everyone? It's that when we have these arrays, instead of taking a literal array and changing its size every time we do the merge sort, instead what we can do is we can divide our array by just saying our divided array is not going to be a whole new array. It's not going to be an entirely new array object. It's just going to be a range of indices in our original array, right? So our range of indices is, well, it's going to be like, this one's going to be from 0 through 3, right? Because 38, 27, 43, 3. That's going to be array index 0, 1, 2, and 3. Does that make sense to everyone? Are there any questions about that approach? Or do you guys disagree with it? What do you guys think? So instead of creating brand new objects for the array, arrays, we divide it by saying the divided array is the main array at index, let's say, A to B. Does that make sense to everyone? Are there questions about that whole process? Right, or is it unclear? Do you guys want me to explain again maybe what we're doing? We're, instead of dividing the array literally, we will instead just calculate the index we need for the divided array. Like, what index do we need to access our original array at for it to behave like it was the divided array? So how would we do this, right? Well, why wouldn't we just create, well, we can have two indices that we pass to this, right? We want the index where we start, and we want the index when we end, right? So we can say int start index, int end index, and idx, right? Now when we call this, we'll just pass it our array length and 0. So this is by default 0, and this is by default our array length. We can just pass those every time we call it to start off our recursion. And then we can say, for example, if, right, how do we identify a base case? Is there, now we have, instead, our divided array looks like this. Our divided array equals array from start idx to end idx. So that's how I'm going to define it. Our divided array is that. So how could we tell if our divided array is at the base case? How do we know if we've reached our base case? I asked you before, how do we know that we're at the base case of our division? So this is the same question again. How do we know we're at the base case? Right. One of you guys say if the start index and end index are the same. Could you explain why the start index and the end index being the same would be the base case? Yeah, exactly, yeah. Yeah, that's great, exactly. So it will be if the start index is equal to the end index. And another way we can express our base case, well, we can do it like that, right? We can say if start index is the end index. What do we do? Well, actually, we do nothing. We're done dividing. So here we do nothing. Nothing. And now else, if they're not equal, what do we do? Well, we have to divide. So what we could do is we can actually, one of you guys before, you said divide into 2 by the middle as long as the base case isn't repeated or reached. So could you explain what you mean by divide into 2 by the middle? Right, so we want to divide our array, right? So how could we do that? How could we use this to recursively divide our array? You say set the index to the mid plus 1. So could you elaborate a little bit more? How do we calculate our mid, and why do we do our mid plus 1? Well, let's think about it, right? So our array needs to be divided in half. So here we have an array with lots of crap in it. We got to divide it in twain. We got to split it up into 2 pieces that are equally down the middle, or if we have an odd number of stuff, we'll just take the first one as bigger, right? We don't actually have to do any logic for that. All we actually have to do is a very simple step. We'll say int mid index is equal to, let's say, the average of our 2 indices, right? We want to sum our 2 indices to get the point in the middle of them. So that would be start index plus end index over 2. So here we calculate what is in the middle of our array, or our 2 indices, or what is in the middle of our new array, right, of our subarray. Does that make sense? We're just dividing it into 2. We've got our middle index now, which is the center of the array, and that's actually how we're going to split up our array further. So could somebody tell me, what would the recursive call be here, right? So we have our arrays now kind of split, right? So could somebody tell me how would the arrays be split? Like, what would the two subarrays be here, given that we have the min index, the start index, and the end index? And how would we recursively call to split them? Again, my question is, so what we have is here. We have a mid index, or a start index, start of the subarray, or mid index, the middle of the subarray, and then we have end index, end of the subarray. So how do we use these three things to recursively split our array further? So, you can send the end index to the middle. Okay, sure. So one of our steps, we could say, is that in a recursive call? Do you want us to recurse with the divide call, right? On the same array, but then to using the middle index as our new end index? Is that correct? Okay, so we'll call divide on array, and we'll say our start index will be the same, so we'll say start index, and then we'll go mid index. Sure, that makes sense. So what will this do? This will go and split the first half of our array more, right? So every time it's going to split in half, kind of like a tree. So the way we have this, it's going to look a lot like that. The top half of this thing here is going to look exactly like this kind of splitting path. It's going to split the big one into two. It's going to split each of those two into two. Then it's going to keep splitting them, right? For the 10, it's going to do nothing because it's already split up. For the 9 and the 82, it's going to do something. It's going to split them up. And then we're going to continue until we get everything divided up. So that's one of the cases, right? And what's the other one? So we've split our first half. I see that you're saying repeat the recursive formula with input start index, mid index plus 1, end index. Could you explain why we do mid index plus 1 in that situation? Yeah, exactly. You're right. It's because we'd have overlap, right? If we start at mid index on the second one, then the second one and the first one would share that one element, and we'd actually get into a stack overflow. Do you know why we'd get into a stack overflow in that situation, or why we could get into a stack overflow in that situation? Oh yeah, it's because we have two things of length 2. But then we might have an array of length 2 which has the same items. So actually, no, maybe we wouldn't get a stack overflow. But we would get some real ugly situation. We could get a stack overflow, or we could have it so that we have another extra element and our arrays would grow. And then that would not make any sense, right? Because our array would try to squeeze an array that's too big into our original one. Or we'd stack overflow because it would never stop the recursion. Because, well, the start index will never equal the end index, because it would keep supplying the end index and the start index being different into this method, and then eventually it'll do one of those two things. Otherwise, it's going to be ugliness, so that's a good call. We should definitely do mid index plus 1 and end index. And now we have a division algorithm. How do we check if it works? Well, maybe if we get to our base case, I'm going to print it out. So I'm going to say system out print line, and I'm going to say, well, actually, maybe I'll get my array done first. So I'll say for int I is equal to start index is less than end index, I plus plus, or I guess less than or equal to. And then we're going to say system out print line. I know it's telling me that it's a bogus for loop, but it's just to make sure that in case we have more stuff in our array than we expect, we'll print all of it, and we'll say array at I. Right, and then we'll also say system out print maybe right, okay, so now let's see. Can we run this? We're going to say public static void main string args, and we'll say, let's create an array. So let's put some numbers in it. Let's just say int room test is equal to new int, and we'll have it filled with some random crap. So let's put in like this is the button mashing random number generator, where we bash random buttons on the keyboard to see what numbers will come out of it. Now we don't care about it being sorted, we just care that it divides into its individual pieces. So now we can call divide on test from 0 to test.length. Length, and now let's see if it works. Hopefully it does. Right, we're gonna run. Oh no, it doesn't. All right, index out of bounds exception. Oh, because I forgot to say -1. Let's just do that. So we gotta remember that when we work with our indices, it's length -1. Common mistake, I make it all the time, so does everyone. It's just kind of an annoying thing about arrays. Now we still have index 11. Why is that? Start index is greater than end index. What could our issue possibly be? Now, why are we getting index 11? Well, that's a fantastic question. Let's figure it out with the debugger. But also, let's just see if it works. So we're getting 214, 23, all the way up till 4. Then we just have it so it's 1 too big. Right? We go from start index to end index. Start index is greater less than end index. Mid index +1. It all looks okay. But our if condition isn't exactly the strongest. What we actually might want to do is we might want to say that if, well, we'll swap the order of if and else, and I'll tell you why we do this after we do it. So we're going to swap these two, and we're going to put this into our else case. Then what we can do is we can say if start index is smaller than end index. And now if we run it, hopefully we'll avoid the array index out of bounds exception. We don't. Okay, we'll fix that. But also, by doing this, we're actually able to see that if our indices go too small or too big, we'll also catch it. So if for some reason somebody makes an invalid call where they're going from a negative start index and like a positive end index, or like an end index that is smaller than the start index, there's an issue. But of course now we're seeing an array index out of bounds exception. Now we can use the debugger to figure out why it's happening. So let's go into here. Where is it happening? It's happening on line 43 here. On system.println array at I. I'm going to go into here. Okay, so we're reaching a base case, but there's actually nothing in the array here. So we're going to go until the end, so we can see we're printing out all our various items. 9. Okay, we're at index 9. Our length is 10. So this is the last valid index. So I think it's just an issue with our printer. It's that it's also identifying that, of course, the indexes are not the same for the last item, but since we have an odd number of items in our array, or is it, yeah, since we have, no, we have an even number, yeah, no, we have an odd number of items in our array, right? So since we have an odd number of items in our array, we are going to have one of these as blank. So that doesn't actually matter for our sorting, but the reason we're getting an array index out of bounds exception here is that our divide algorithm is saying that if our start index is, well, if it's going to be the opposite of this, so if it's greater than or equal to our end index, so greater than or equal to end, then we're going to enter this situation. And start is greater than or equal to end as well in the situation of I equals 10, right? Or no, I equals 11, right? I equals 11 meets these conditions. Doesn't matter though. And it doesn't matter for merge sort because in merge sort, we actually don't use this part of the loop. In merge sort, we just finish dividing and then we build it back up together. And once we build it back up, we don't care if whatever is there is nothing because, well, there is nothing at that point of the new array either, right? So we're not going to try to fill up the array at an index 11 if there's nothing there. And we don't stack overflow, so it's actually, like, it's okay. This is just kind of an improper use of the recursive algorithm, but we have shown that our dividing works. So are there any questions about the divide algorithm here or any of how we're dividing our array into small little chunks? Again, any questions about this divide system, right? Any questions about how we're taking our array and we're dividing it into the base cases? All right, great. So now we finished with the divide step of merge sort. and we can move on. So here we've got our divide step. This is a bit of a slide explaining it. I guess maybe I should have gone over the slide before I went over the actual implementation, but that's okay. Slide is still quite relevant. So first off, we're just going to go through it really quick. So we divide our array. We already know this. We're experts at this already, right? We split our array and we divide. We keep dividing. Why do we divide? Because it's easier to sort a array of a smaller size, right? Something of size 1 is already sorted. So we're basically splitting up our array into sorted pieces. And now the time complexity. Now that is a good question. Could somebody tell me what is the time complexity of dividing our array into these little pieces? You say log base 2 of n. So why would it be log base 2 of n? Okay, but so you mean that every time that we divide our array, we split it in half, right? And then, so we can see here on this diagram that as we divide, we start dividing things that are half the size each time, right? So we divide the first one, right? And then one step brings it to half of its size. The next step brings it to another half of its size. So mathematically speaking, how would we express where each step will divide the amount of things we have to do by 2? Or more accurately, like, how do we express mathematically, let's say, if the number of steps we take is inversely proportional to 2 to the power of the size, right? Because let's think about how many elements we process. Well, instead of thinking about how long it takes to process each element, let's think about how many steps we have to take to process each element. For something of size 1, we have to take 1 step, right? Something of size 2, we have to take 2 steps. Something of size 4, we have to take 3 steps. Something of size 8, we have to take, 4 steps. So if I'm going to make like a little table here, in fact, I'll do that now so we can just see. I know the theory of it's going to be on the quizzes, so it's good to go over it a little bit for time complexity, and we'll get into that. So that's not the right. I need bash. Okay, so come on, open up. There we go. All right, so we say that to divide an array. So size 1, let's say it takes 0 steps because it's already divided. Size 2, right, it would take 1 step because you just need to divide it in half. And now size 4. Size 4 would take 2 steps because you divide it into things of size 2 and then size 1. Size 8 will take 3 steps because you divide into 2 4s, which each divide into 4s, which divide into 2s, ... Right? So as we increase our size, the number of steps we have to take, like the depth of our algorithm, increases quite non-proportionally to how long it takes, right? That's why it's n log n. Right, because we can see the relation of exponents here. We can see that since we divide what we're working with in half each time, adding on another, like doubling our size again, will not double our time complexity. Doubling our size again will just add 1 step to our time complexity. Right? Again, so doubling our size adds 1 step. That's a good way to think about it. And maybe if you guys see other algorithms where doubling your size will add 1 step, you could say that it's a log base 2 of n, or we just say log n because we assume log base 2 usually, of n time complexity. All right, that's great. So we've got that, and now we can move on to our next step. So we've got our base case now. We already identified our base case. Now there's one thing different in merge sort versus what we did. So could somebody tell me what is the difference between what we did and the base case in merge sort? It says it on the slide, but maybe if one of you guys can say it and if you understand it, you can get a bit more detail on it. So could somebody tell me what is the difference between what we do on our base case and what merge sort does in its base case? All right, again, so what here is different between what we did and what's in merge sort? I'll show you what we did again. So what we did was here. We were dividing it, into its little pieces, and then we were doing nothing with the pieces. So we just divided it, or we either did nothing or we printed. So is there anything we have to change anywhere in our method to turn it into merge sort? What is the difference between what we did and what merge sort does? Well, merge sort doesn't just divide, right? Merge sort also merges things together. Merge sort also actually combines the array back together. So the difference between what we did and merge sort is only one line. In merge sort, after we reach our base case, we have to put everything together, and then we pop back through our stack and we keep putting everything together. Now, what I mean by this, we can actually figure out here in the merge step, and we can also figure it out by looking at our debugger to see what's on our stack. So could somebody tell me, just before we get into the explanation, could you give me a guess as to why it is when we do our merge step, do we care about what's on our stack? Why do we care about what methods we called before recursively? And how could it be that we will merge all of these subarrays back until we get to our original array? So how could you explain that with recursion and thinking about the call stack? Remember, we saw things like this before. Like in the Fibonacci algorithm, we saw that we pop through our call stack and we do our work, right? So if I go back towards, to recall Fibonacci, we remember that in our Fibonacci algorithm, we had this sort of tree. And then as soon as we popped up from one part of the stack, we had to push down into the next part, and we then kept sorting it, or we kept doing the Fibonacci algorithm. We can do something similar with merge sort. So what we do is we call our method, our sort method, and it pushes all of those sorts to the stack, and then we gradually pop back out. We say we assume that all the small lists are already sorted, and then we use two parallel pointers. Yes, we do assume they're already sorted, but I don't know what you mean by parallel pointers. Could you elaborate on that? Yeah, you're right. That is actually something we'll have to do, but that's actually more in the implementation of the merge sort. You're right, completely. It's just, maybe I didn't phrase the question perfectly. What I'm actually wondering is not how the merge method works, but how is it that we call the merge method? How is it that the merge method knows that it has to combine each subarray into like the bigger ones? How does it know which things to put together? It's something that confused me when I was first writing this, and because I feel like it was kind of not covered. But understanding it will actually help us understand a lot more about how a merge sort will work. So again, the question is, how does merge sort know to take the reverse step? Like, how does it know to put the array back together in the same order that it took it apart? Yeah, okay, you're right. So let's take a look at that actually in the debugger, and let's get a very quantified understanding of what we mean by these things are on the stack. So if I enter the divide method here, I put a breakpoint on it, and I'm going to run it with the debugger. Stop and rerun. We're going to watch as it divides, and then we can watch it as it pops back out of the stack. So again, see where my mouse is here under frames? That is what we consider our stack. So every time I run this, you can see it pops onto the stack. So then we have 1 and 2. That's our depth. So that's how many times it was called. We're gonna divide this, right? And actually, before I run it all the way, can somebody tell me how many times do you think that this divide method is gonna have to be called to completely divide our array? Understanding that it's log-based to event. So again, how many times, like what depth are we gonna reach of the divide so that we fully divide our array is my question. Okay, you say depth 3. Well, we're already at depth 4, so that's probably not it, because remember, we still call it the first time when we give it our entire array. So, yeah, you're right, we get to 3 kind of, because I see what you mean. Like, we split it 3 times, maybe? But what we're actually doing is we're getting to a depth of 4 so far. Let's see, do we get any further? No, we actually get to depth 5. Right? And the reason we get to depth 5 here is that it is gonna get to our base case as well. So see, it has 0, 0 here as the start index and the end index. So we actually get to the case where these two things are equal to each other. So that's a depth of recursion. I'll take you through our steps, right? So first off, we started our first level of recursion. This is when we first call our method, and we can see here, I've highlighted, start index is 0, end index is 10. So right, this is our first level of recursion, 0 and 10. We've got the whole array. We divide it in half, which brings us to 0 to 5. We divide that in half, which brings us to 0 and 2. We divide that in half, which brings us to 0 and 1. So these three are, yes, as you said, one of you guys said it was 3 steps. That's kind of, you can see how you would think that, because here we've got these 3 where division actually occurs, right? Division occurs here, here, and here. But it's actually more than 3, because first we have to divide our whole big array into the 2 subarrays. Then we divide, and we divide, and we divide, and that's proportional to the size of course, our array. And then we eventually get to our base case, 0, 0. This is technically also a base case of length 1, but the way that our recursion works is it takes us to an extra depth where the two things are equal to each other. Not really to make sure, but more so to just make our code shorter. And then, of course, we start popping through. But when I start popping, are we just going to go 5, 4, 3, 2, 1, or is stuff going to be pushed to the stack? Like, are we done here once I go through this recursion? When I click next, are we going to go back to 4, then 3, 2, 1, or is it going to do something else? We're going to go to the second recursive call. Yeah, exactly. So we're not going to completely go back up. We're actually going to go 4, and then, well, we do pop back in 4, 5, and we do that every time. So right, we go 3, 4, 5, and we go back to depth 5 each time, because we do that second call. So we're going to go bam, and then finally we're done. So if you look at actually how our recursion works, maybe every time what we recurse is we can print out our start index and our end index. So every time it's not the base case, so every time we split, we'll do a print system.out.println. Start is going to be our start index plus end is going to be our end index. And we run this, and we'll see kind of how we go through. So we first go, 0, 10, 0, 5. We split the first halves until we get to the base case. Then we start splitting the other halves, 3, 5, 3, 4, 6, 10, 6, 8, 6, 7, 9, 10, and then we're done dividing. So these are all the times we divide, right? And then let's say we put something after this. So we'll say system.out.println. Now we have, well, what do we have? Let's say start index. So start is start. We'll copy the printout from before actually. So start, and okay. So we'll copy that print line from before, and now let's see what order it's going to show up in. And we can actually see how our merge sort does it. So we go 0, 10, we start, and then we end at 0, 10. So hold up, how come we print, like, logically, it should print, 0, 10, because start is 10 and end is 10, or end is 10, start is 0 for the first time, right? And then why doesn't it print 0, 10 again in the same method call, right? So we're in this method. Let's assume that it's going to be the first time we ran it. We didn't do any recursion yet. Why is it not printing 0, 10, 0, 10? Why is it instead printing 0, 10, and then everything else, and then 0, 10 again? Could somebody tell me, why is it printing our first thing in these two different places? One at the start and one at the end. Well, it's because before we're allowed to print these again, right, we have to actually divide everything else. So the first thing we do is we print the start and the end. Then we do all of the other divisions recursively, and only when we're finished every other division do we start being able to pop out and print these things. And that happens recursively. So for every single one of these until the base case, we only do this print if we're able to. We'll only do this print once we're done all of the divisions that have to happen previously. Does that make sense to everybody? How this is where the step happens to merge. This is where it goes in the reverse order. It's this second print line. So this is the part when merge should happen, because all of the previous divisions are done. Previous divisions and merges will be done. Right? Because it literally happens in the order that you write it, right? It goes 37, 38, 39. That's the order the lines run in. So line 22 is going to run, then 37, which is recursive, and 38, which is recursive. So it's going to finish both recursions before it gets back to here. Does that make sense to everyone? Are there any questions about how that works? Why it is that the print lines take on this pattern, where we go from 0, 10 at the start and then 0, 10 at the very end? All right. Well, I know it's a bit of a confusing topic, so I won't dwell on it because we do have to get it done. But if there's any questions, by all means, let me know. But just know that the reason that we're gonna merge at this step is because this is when our divisions are right, and then as we pop back out of our call stack, we are gonna make sure that it's mirrored and go through, and it's gonna like put it back together in the correct order for us. All right. So that's why we have this merge taking place, like it shows in the pink. So why don't we get to it? Our merge step is going to be maybe our most involved step. I'll just write our method header for it. So we'll say public, what is it, static void merge. And actually merging is also where the sorting occurs, right? So in merge sort, we don't actually compare any of our elements during the divide step, right? We actually compare our elements during the merge step. So we'll take our array, so int Badum array. We'll take our int start index, int end index, and we'll put it in here. And oops, I put my method header in the wrong spot. Let me put it where it belongs. Okay, so we've got our array, our start index, our mid index, and our end index. I forgot my mid index. Let's put that to here, int mid index. Now this is going to merge everything, right? It's going to merge the two subarrays. It's going to merge subarray 1 and 2. So the job of merge, right, is to merges two subarrays. Now which two subarrays does it merge? Well, it actually merges the same ones we just divided. So it's going to merge mid index plus 1 to end index, and so these two. Which subarrays does it merge? It merges these two subarrays. Not with 2 stars, I want it with 1 star. Divide, right? So it's going to merge these two subarrays. Does that make sense to everyone? We're merging the two subarrays we just divided recursively. Now we're going to merge them. And in fact, I'm going to add our merge call here. We're going to say we're going to merge array, start index, mid index, end index. Right? So we're going to merge those. So before I merge those two subarrays, what can I do? What can I do to have these two subarrays as actual arrays? Right? At this point, my arrays just exist kind of in my imagination, right? So right now, let's say array start to mid and array mid to end are just ideas, right? They're just in my imagination. So how do we make them real? Well, let's actually create them, right? Let's create arrays that are from the start, or from from the start index to the mid index, and then from the mid index to the end index. So let's create those. Let's first calculate their size, so how big the arrays are going to be. We can say that, well, the first array, the one from start index to mid index, would be very simple, right? It's just going to be end index minus mid index. Why is it going to be that size? So it's an int size of 1. Size of 1. Maybe size of A is going to be that. Equals end index minus mid index. And then the other one will be mid index minus start index plus 1. Size of B equals mid index minus start index plus 1. Now, why do we do this? Because, what we want to do is we want to say that this array is the array going from, so this one is going from 0, or from start, or yeah, from start to mid, and this one is going from mid plus 1, to end. right? So we're calculating their sizes. Those will be the sizes of our two array. And then we're going to actually have to copy our arrays over. So we're actually going to create new arrays. So we're going to say int badum a is equal to new int size of a. And maybe a should be lowercase for convention. Int a. Now int badum b. And honestly, I hate these variable names. I'm going to change it to something more descriptive, actually. New int size of b. And maybe a and b should be upper half and lower half. Let's just do that. So int lower half, int upper half, just so that we can make more sense of what's going on. Now we have our two subarrays. We're going to fill them up with elements from our main array. So we're going to say for int I equals 0, I is less than lower half dot length, I plus plus. And then all we have to do is fill it up. So we can say that it's going to be of the start index, or not dot length. Yeah, we can do it like that. And then we can say that lower half at I is equal to start index plus I. Right, because this one is going from start index all the way up to our end index. So this is going to go, or start to mid. Right, now upper half is going to have the same thing. We're going to have for int I equals 0, I is less than upper half dot length, I plus plus. We're just copying over into these arrays. We're taking these arrays from being imaginary to being real. We're saying upper half at I is equal to mid index plus 1 plus I. Why is that? Because our start point is mid index plus 1, so it's going to be mid plus 1 to end. So that's going to be our two subarrays. Does everything above make sense to you guys? Does this entire procedure all make sense? Why we're doing it and how we're doing it is all clear. So we're trying to merge the two subarrays, these two, from our previous recursion. And we're going to do that by actually creating the arrays literally, like that. And then we're going to use those two arrays to merge them together. Does it all make sense to everybody? Are there any questions about this step? So anything at all? Could somebody tell me, why do we do this? Why do we create these arrays in memory? Why do we need to take this step? Well, if we're gonna merge back into our original array, so next we merge into our original array. Well, how do we get, these are temp variables basically, right? To be able to merge into our original array, we need to remember what was in those indices before. So right now, imagine we said that array from start index to end index equals temp equals upper half, lower half. Does that make sense, right? So we're basically taking whatever is in our original array from the index start index to the index end index, and we're creating a temporary variable, or actually we're creating two temporary variables, which are upper half and lower half. And also, we know that upper half and lower half are sorted. Why? Because recursion, or because of the recursion we did above in divide. Right? So we know that we've split up our array from start index to end index into two halves, upper half and lower half, which are temporary variables, from which we can then refill our array from start index to end index. Is it all clear to you guys? Does this step all make sense? Or is there something that you'd like a bit more detail on? Again, is there anything that you would like me to re-explain? Anything about this step that was unclear, where we just create our new subarrays, or is it all good? Okay, so if it's all well and dandy, what would be the next step? So how would we start about actually refilling our array with the elements from our sorted subarrays. So we have upper half and lower half, which are sorted. What do we do next? How do we take these sorted halves and refill our original array with their contents? How do we say, so what we need to say is our array from start to end equals elements of upper half and lower half in order. So how can we do this? How can I make it so that my array from the start index to the end index is equal to the elements from upper half and lower half in the correct order? We compare elements using parallel pointers. Could you elaborate on that, kind of what you mean by comparing elements using parallel pointers? All right, so how would that look in terms of loops? Like, what kind of loops would we have? Would it be a for loop, while loop? How would you structure that with the parallel pointers? All right, so let's do that. So we've got a while loop, and what would our while conditions be? Like, what do you think? You don't have to do them exactly, but like, what do you think logically the while conditions would be for this kind of situation? Well, we have these indices, right? So you say we have parallel pointers. Let's say that we have an int index at upper half equals 0, int index at lower half equals 0, right? So we've got these are our parallel pointers. Boom, boom, parallel pointers here, right? In case you were wondering what those would look like, this is what they look like. We have two different references. You're storing the index at each array. Now we also want to keep track of our index at the main array. So also this int index at main equals start index, right? Do you understand why we have this? Index at main is start index. So why is this here? Why is this here? Again, so we have to track three indices. We track the parallel pointers, as you said, but we also have to track the index in our original array. Why do we have to track the index in our original array as well? Why do we have three parallel pointers instead of two? If we're only copying from two subarrays, why do we have to have a third index from which we are copying? Why do we have to have that? To know where to add it back into the main array. Yeah, exactly. So, yeah, you're exactly right. This is where we go in. So this is where stuff goes in the original array, and this is where stuff goes. So where we are at in upper half, and this is where we are at in lower half. Now, back to the while condition. Now that we know these are three variables, what could we say that our while condition has to do? How do we avoid our index being out of bounds in our while condition? Yeah, assuming we're using these three things to loop, right? We're going to loop through our arrays using these three variables. How are we going to do our while condition? Such that the loop is going to run properly. Again, maybe we have to do all of these various things. Well, we've got two arrays that we're accessing here, right? So we've got index at upper half and index at lower half. So what we got to do is we got to make sure index at upper half and lower half are both not too big. So we can say while index at lower half is less than size of A. I think A was lower half, right? Yeah. And index of B, or index at upper half, is less than size of upper half. Not a comma, I need an and. Wrong language. Oopsies. And is less than size of B. Right? This way, we can avoid our null pointers. Now it's giving me some yellow. That's because I have not incremented these pointers yet. So inside of here, you said we're going to use the parallel pointers to compare our items. So what do you mean by we're going to use the parallel pointers to compare our items? What does the body of our while loop look like? How are we going to compare things? Yeah. Yeah. All right. Sure. And just quickly to elaborate on that, when should we increment the index at lower half and index at upper half? Right. So when do we do each one? So when do we increment our index at lower half? When do we increment our index at upper half? We have this issue here that says variable index at upper half is not updated inside loop. So where do we update this inside loop? Well, we're doing two traversals, right? So here we traverse upper half. And then I guess else, right? We traverse lower half. Lower half. So here we can do upper half, index at upper half plus plus, right? Because we're traversing through the upper half. And here, since we're traversing through the lower half, we can say index at lower half plus plus. And then, of course, here I'm also able to say that the array at index at main is going to be equal to the lower half at index at lower half. Now, if you guys are using crappy variable names like a and b, this is going to get really confusing. So you make sure you use good variable names. Sure you have good variable names. It's long variable names, so if you don't use like code completion, they can take a while to type. But it's much more clear to say lower half at index at lower half than to say, for example, as a lot of professors would say, you know, a at x or something, or some crap. Right? So just to make sure that everybody understands, when you might see something like that, right? Like a at x or a at I or something, right? Or a at j. What they actually mean is this. Index at lower half is, like lower half at the index at the lower half goes into the array at the index at main. Now, before we iterate anymore, we also have to say index at main plus plus. And I've got one question for you guys before we conclude the merge sort. Why do I increment index at main, but not check if it's outside of our bounds? Like, why do I check if index at lower half and index at upper half are smaller than the size of each thing? So why do I not get an array index out of bounds exception for index at main? I mean, my index at main could technically increase to infinity, and this while loop would not stop. So what's stopping index at main from going to infinity? And why do I not get an array index out of bounds for my main array? Main is dependent on upper half. Well, yeah. What we're seeing here is that the index at lower half, size of A and size of B, right? These are all bounded by the size of our array. So size of A and size of B, so size of A plus size of B are never more than array.length, right? Why is that? Because A and B are generated as subarrays of, well, array. So if we are within lower and upper half, we are therefore within array, right? That's why we don't care about this index. So if we are inside subarrays of array, we must also be inside array, so this is not checked for in the while loop. All right, so that's that. That's just another potential question we might see. Now that we're done, do we have to do anything else, or are we done? Well, a simple question here. Are we finished with merge, or is there something we're missing? We've done all the stuff. We've put our elements back into our original array. Is there any step we still have to do? Well, if we run it, and to run merge sort, it gets called in our divide method. So all we have to do is we have to run divide of our array, and then we can just system.out.println array.toString of test, right? So now if we run this, we should see test is in order, right? Or is it going to break? So 6, 7, 8, 9, 10, 11, 9, 10, 11, 10. So that's not working. Is there something we're missing in our method? Again, we ran it, our merge sort looks fine, but when we run it, it looks as though something is missing because our stuff is out of order. Is there anything we can do to fix that? Well, what we're missing is what happens when we leave this while loop. What if we finish with A, but still have stuff in B? Or what if we finish with B and still have stuff in A? So we are left with a case where B still has stuff or A still has stuff. So what we have to do is we have to flush out A and B. So we have to say while index at lower half is less than, or A or B, where upper half or lower, where index at upper half is less than size of upper half, so size of A. The data set, or our array, at index of the data set, obviously, is going to be index at left, and then we increment both. So index at lower half, array at index at main, actually. Index at main is going to be equal to array at index at lower half. And now we can say index at lower half plus plus, index at main plus plus. And now this is just going to flush out the remaining stuff in each one. So we're going to do the same thing for our upper half. Index at upper half is less than size of B. And then index at upper half. Index at upper half. Okay, so now we flush out our arrays. And when we run merge sort, let's hope that we get a fully sorted array. And 6, 7, 8, 9, 10, 11, 6, 7, 8, 9, 10. So it looks like our merge went wrong somewhere, and that's okay. We can hit that with the debugger, and we can see what's going on. So we increment our index at dataset, index at 0, start index, size of B, blah, 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 blah. Do we call our merge in the correct location? So we do end index, start index, mid index is that. Don't see anything obviously wrong in this, but clearly something is going wrong at the end of our recursion when we're about to merge together our final two arrays. Clearly something is off with that step. So
one eternity later.
Alright, so after a decent amount of debugging, figured out what the error was. It was just a silly typo here where I meant to say index at lower half and index at upper half, I actually said index of array. So what was happening was in the situation where we were copying from the end, it was copying from the original array back to itself instead of saying from lower half and from upper half. Alright. So assuming you guys have no questions, well, thank you for coming and enjoy the day. All right, see you guys later.